at the end of the lesson, you are going to define the differences between eigendecomposition and singular value decomposition. 2. Follow the process of identifying singular value decomposition. And 3. Appreciate the significance of singular value decomposition. In this session, we are going to explore the singular value decomposition, or SVD. So just like the eigendecomposition that we had in our last session, the link is given if you would like to watch or study lesson number 9. It's given in the description below. So we will learn another form of, or another method of matrix factorization, and this is called, again, the singular value decomposition. So also, just like eigendecomposition, the singular value decomposition can help us discover some information. So just like your eigendecomposition, wherein we discovered some properties of certain data, a certain object, singular value decomposition would be able to tell us also some information about a certain set of data. So, but the difference is that SVD is more generally applicable. So we have here, it's general. So maybe you would ask me at this point, what makes this generally applicable? Okay, so the fact is that all real matrices have SVD. Again, let me repeat that. All real matrices have SVD. So in the case of eigendecomposition, it is not possible to apply this method in all situations because the requirement for a matrix for eigendecomposition to be applied is that it must be a square matrix. Remember, in our last session, we talked about a square matrix. So that is in lesson number 8. So just to give you a short review, a square matrix has the same number of rows and columns. So if a row has if a matrix has 2 columns, the row needs to have 2 columns too. Okay? So as to the process involved, eigendecomposition and singular value decomposition each has its own processes or process. So in decomposition or eigendecomposition, we analyze a matrix A. For example, we have here. We analyze a matrix A to know the matrix of eigenvectors, to know the eigenvectors and a vector of eigenvalues. So we have this concept statement A, then we have U, this is diagonal, and then we have the transpose of the matrix U. Okay, so SVD on the other hand is actually more or less similar to this one, but in this case what we do here is that, as you could see, U, diagonal, V, then the transpose of V. So maybe you would ask me at this point, what's the meaning of this one? What's the meaning of this, this, and this? So we discussed about this one, so just go to lesson number 9 if you would like to know more about this. So let's examine SVD. So what's the meaning of each element of this statement? Let's start first with this one. What is this? So U is an M by N, and the column is orthogonal. So its columns are eigenvectors of AAT, AA transpose. What about V? So V is N by N and orthogonal. So it means that its columns are eigenvectors of A, T, A. So maybe at this point of our discussion, you would find it hard to understand AAT, ATA, but as we go along later, as we go step by step of the process of SVD, we would be able to understand what do they mean. So now let's have the D. What is D? Or the diagonal? Okay, anyway, in some cases, maybe sometimes, let's use another color. Maybe sometimes you could see this kind of symbol and then this symbol. Okay, they're actually the same. So they mean diagonal. So, but as of this moment, we will just use D. Okay, we will just use D for consistency of our lesson, so we will not get lost as we go along in the process, right? So as you notice in this case, or anyway, D, we are not yet done with D. So D is an n by n matrix too. So D is an n by n matrix, and this is a diagonal matrix, which means it's a non-negative real values, which is called, or which are called, singular values. Okay, so later we will understand what these singular values are. Okay, so there could be some other differences between eigenvectors, eigendecomposition and singular value decomposition, but as of our discussion, we will just have three. Okay, so if you would like to research more, of course you can, and please comment your information below so we would be able to discuss, and some of the viewers of this channel would be able to see too, and we could have a very rich discussion about the differences between eigendecomposition and the singular value decomposition. So for better understanding of the singular value decomposition, let's have this example. And so let's consider this matrix. So we have the matrix A, -2, 0, 0, -1. So what we will do? So let's go through the 6-step process for us to be able to understand how we arrive to the singular value decomposition. Okay? So our first step is to find the eigenvalues of matrix A transform A. So what is this? So first is that we're going to transpose this matrix. So we have this transpose, and then this is this. So as you could see, they have the same order of values. It's because this is a square matrix with 2 rows and 2 columns. So most likely it would have the same order when you transpose it here. Okay, so when we multiply it, the A transpose and the A, then we'll get this one. Okay, so because the matrix is diagonal, still remember diagonal matrix, that is in lesson number 8. In a way, the link is given in the description below, so please watch it. Again, because this matrix is diagonal matrix, it is now easier for us to find the eigenvalues. So maybe you would ask me, where are the eigenvalues in this case? So the eigenvalues are the numbers in the main diagonal. So let me encircle the main diagonal. So we have here, we have 4 and 1. So the eigenvalues, again, are in the main diagonal, and in this case we have 4 and 2. So eigenvalue number 1 is 4, and eigenvalue number 2 is 2. Okay, so after getting the eigenvalues, the next thing to do is that identifying the singular values of A. Again, we're going to identify the singular values of A. So how to do this is to get the square root of the eigenvalues of A, T, A. It's very simple. So all we have to do again is that we're going to get the square root of the eigenvalues of A transpose A. So we have here. This means, maybe you would ask me before we go further, what is the meaning of this? Because when you go to your statistics, they would mean different thing. Okay, so in our case, for this session and for the study of eigendecomposition, this symbol is singular value. Okay, so singular value number 1, square root of 4, of course it's 2. Singular value number 2, so we have the square root of 1, and of course we know that the square root of 1 is 1. So take note that we always name the singular values in a decreasing order. Okay, so because we always name that in a decreasing order, so that's why we start with 2 and then 1. Okay, because 2 is higher than 1, and then this is decreasing order. So our third step then is to write our diagonal matrix. So be careful in writing this kind of matrix. Why do you have to be careful? Because we will always have to take note that it has the same size as matrix A. So let's go back first to matrix A, because our consideration in writing the diagonal matrix is that it needs to have the same size as A. So the size here means the number of columns and the number of rows of A. So A has 2 columns, 1, 2, and also 2 rows, 1, 2. So, and also, another thing is that it contains the singular values. So what are our singular values? So our singular values are 2 and 1. So where are we going to put or write the singular values? So we write the singular values in the diagonal. See? So we have 2 columns, 2 rows, just like A. And the singular values, 2 and 1, can be found in the diagonal. Okay, I think that one is made clear. Now, let's go to the fourth step. So if you have some questions, you can just write your question in the comment below. So what shall we do then after having 1, 2, 3, 4? Okay, so let's go to step number 4. And our step number 4 says that we're going to set up a V. So where is V? Remember V? Okay. So how are we going to set up V? So basically what we do here is we find the eigenvectors of A, T, A. So these vectors are what we call the right singular vectors of A. Again, we call this the right singular vectors of A. Let me write here for you to be able to see. Okay, so right singular. So later I will explain to you what makes this right singular vectors. So after we are done with the decomposition. Okay, so because there are 2 eigenvalues, we should expect that there should be, or there must be 2. Again, there must be 2 eigenvectors. Okay, now let's start first with the first eigenvalue. Our first eigenvalue is 4. So we have this A transpose A minus 4 I, which is equal to 0, 0, 0, negative 3. And that means if we're going to go further, we have 1, 0, which is the eigenvector for the eigenvalue 4. And maybe for some of you don't know this one yet, let me take you to the basic one. If you could not remember, then remember we have 4, then we have 0, then we have 0, and then we have 1. Maybe you would ask me, where did we get 4, 0, 0, 1? Okay, let's go back. Okay, this one, right? So this is our ATA, okay? And then it's because our first eigenvalue is 4, then we minus that. So minus 4, minus 4. That is why we get 4 minus 4 is 0. 1 minus 4 is negative 3. Of course, 0 here. So we just copy. Okay? So that's it for step number 4. No, we are not yet done with eigenvalue number 2. Sorry. So eigenvalue number 2. So we have 1. Remember, the value is 1. Then the same process and the same way of getting this 1. But in this case, we have 1. So 4 minus 1. 4 minus 1. This is for eigenvalue number 2. So we have 4 minus 4 is 3. And that is 0, 0, because 1 minus 1 is 0. Then, if you're going to compute everything, then we will arrive at eigenvector 0, 1. Okay? So, what we should not forget here is that the matrix V is an orthogonal square, or anyway. So here, what we do for the eigenvectors is that we combine it. We combine it to become another matrix. And this is actually the matrix of the eigenvectors, which is called in our statement V. Okay, so we have 1, 0, which is this one, then 0 and 1, which is the second vector. So what we should not forget here is that the matrix V is orthogonal square matrix. So because it's orthogonal, the size is m by m, so which means it has the same number of columns as the rows. Okay, so again, because we have a V1 and V2 are unit vectors with different eigenvalues, so we combine them to form an orthogonal matrix. So this is our orthogonal matrix. Okay, so now that we are done with step number 4, what will we do now? So we are not done yet. Okay, so after setting up V1 or the V, now let's set up U. So let's go back first to our formula. Let's check what we're done. So we are done with the V1. Okay, we are done with the V. We are done with the D. What about the U? Okay, so what shall we do here? Okay, so how are we going to find each one? So remember that we have two singular values, remember? So let's first go back. Our singular values are 2 and 1. So our step number 5 are really based on the values of 2 and 1. So we have here, let's have first the eigenvalue or the singular value number 1. So this is the formula. 1 here is the constant over Q1 or the singular value 1, then A times the V1, which is equal to 1/2. 1 again is the constant, 2 is the first value or the first singular value that we have, then -2, 0, 0, 0, -1. So where is this coming from? So remember, this is our original A, and then 1, 0, this is our V1. V1 is 1, 0, right? So we multiply that, and then when we do the multiplication, we will arrive at -1, 0. The same process we do for U2, and what we do here is 1 over singular value number 2, which is 1, then the same, -2, 0, 0, -1. This is our original matrix A, and then the V2, okay, our V2 is 0, 1, then we multiply them, and then we arrive at 0, -1. And the same thing that we do in step number 4, we combine them. So here in step number 5, what we do here is that we also do the same thing. So we have u 0, 1, -1, 0, look at this one, for the first singular value, and then 0, -1 for the second singular value. Okay, fun fact. Fact about U. It is an orthogonal square matrix of size n by n. So as you could see, just like this one, this is also orthogonal. Okay, so just like in the previous step, that's what I've said, we combine the unit vectors to form another orthogonal matrix called U. So we could have this one. So in this case, what do you call this value? So if this one is called the right singular vectors, what about this one? What do you call this? So of course, when we have the right, of course, we have to expect that there is always left. So this is left singular vectors. Singular vectors. Okay, now after finding our singular vectors, we are done with U, we are done with D, we are done with V. So what shall we do then? Okay, so our original matrix is -2, 0, 0, -1. So following this composition, now we have -1, 0, 0, -1. So as you can see, this is the left singular vectors. And why this is left? Because this is found at the left of this vector, which is the diagonal vector. And again, in this case, the diagonal vector here is composed of the singular values, which can be found in the diagonal of this matrix. And then we have the vt. And remember, this is the value of, where is this? Okay, right. The right singular vectors. Why right? Again, just the common sense. This is right singular vector because it is found at the right of this diagonal matrix. So the SVD of A can be interpreted in terms of the eigendecomposition of the functions of A. The left singular vectors of A are the eigenvectors of AAT, and the right singular vectors of A are the eigenvectors of ATA, or A transpose A. The singular values of matrix A are the square roots of the eigenvalues of ATA and also for AAT. What is this for? Why do we have to study this? There are actually a lot of reasons why we study singular value decompositions, but for this time, we'll just have two of them. So first is that it is used to partially generalize inversion to non-square matrices. Second, it is used to reduce a large data set to a small one with significantly fewer values without sacrificing the variability of the original set. So after all being said and done, let's try this. What is the difference between eigendecomposition and singular value decomposition? 2. What are the steps in doing singular value decomposition? Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.